Hi, I'm Brian Harris, and this is our project on the history of climate change in Newfoundland and Labrador. Our region is the northeast Canadian province of Newfoundland and Labrador, where we focus on the coastal areas outlined in red in Figure 2. Newfoundland and Labrador reside on the border of the Faroe and Polar Cells and are in a subarctic climate zone. The region is tectonically passive with no nearby tectonic boundaries, but was compressed into a convergent tectonic boundary during the Paleozoic era, which metamorphosed the rock and uplifted Precambrian deep earth rocks to the surface, exposing some of the oldest rocks on Earth. Canada is notorious for its cold weather, and has been for thousands of years. Regional historical sea weather observations have been recorded in logbooks, journals, and novels, all describing sea ice and storms. From the years 1790 to 1820, sea ice plagued the incoming ships, pictured in Figure 3, with 7 of the expeditions late in their arrival to Newfoundland and Labrador. This is consistent with paleoproxy records like tree rings that have low MXD, which indicates a colder climate from 1810 to 1820. Also, the periodical accounts from the missions of the Church of the United Brethren from 1817 stated that for 3 years past, the ship has met with an unusual quantity of ice on the coast of Labrador. Yet, in no year since the beginning of the mission in 1769 has it appeared so dreadfully on the increase. The explanation for the conditions is the eruption of Tambora in 1815, which caused a cooling of the northern hemisphere, so much that the year following the eruption is known as the year without a summer, which is fitting since ice remained along the coast of Newfoundland and Labrador the entire summer, likely until the winter freeze-up. After this decade, things began to look up slightly. Up until the early 1900s, tree rings suggested there were successional warming and cooling periods, which each lasted about 10 to 20 years. Starting in 1832, when the captain of an expedition observed storms and drift ice, which lines up with a day-to-day report of ice from Battle Harbor, which is the blue dot in Figure 4, as well as tree rings suggesting colder summer seasons in the 1830s. As you can see from Figure 5, there are no mentions of anything exceptional between 1832 and 1864, which exhibit a lack of extreme climate. Then, in the 1860s to 1880s, J.P. Newell recognized severe weather returning, and this is also found in the amount of ice found in the Hamilton Inlet, which is the red dot on Figure 4, as well as mentions of late warm seasons by Alpheus Spring Packard. Throughout the 1880s, many cold winters were described in the periodical accounts, and from July 1883 to July 1884, not a single month passed without frost and snow. In the early 1890s, there was a switch to negative North Atlantic oscillation that left the region with a relatively static climate. These historical sea weather records record one aspect of the regional weather of this coastal region, and another important aspect is the historical terrestrial weather.
Hi, my name is Theodore, and I will be presenting on historical terrestrial weather. Historical terrestrial weather is the record of previous terrestrial weather patterns. This can be observed and recorded in several ways: temperature, precipitation, snowfall, wind patterns are all ways of understanding historical terrestrial weather. Prior to the 19th century, most historical records come from proxy data or written observations from the time. These records are vital to understanding climate change and predicting the future climate of Newfoundland. The 18th century was one of the colder periods in Newfoundland history. Tree rings and historical records show that between 1810 and 1820, severe cold seasons prevailed through the year. Tree rings show extremely cold temperatures in 1816, 1836, and 1865, all years that correspond with major volcanic eruptions. Things started heating up around 1925. From 1901 to 1925, we had an average warming and cooling season until the end of 1925, when weather started to get progressively warmer. Increasing temperatures in the century following 1925 has had a mass impact on the coastal region of Newfoundland. Recent winters have seen marked decrease in snowfall and freezing, which has a big impact on the ecosystem and culture. Increased temperatures has also led to an increase in extreme weather events, such as storms and erosion from the increased rain. In the last decades, deaths from extreme weather events like floods, droughts, and storms were 15 times higher than previously in vulnerable regions like the Newfoundland coast. A post-tropical storm named Fiona is a prime example of these increased weather events. The storm swept through the coast of Newfoundland, doing immense damage to the ecosystem and community. From 1775 to 1940, there were 16 tropical storms. In the 81 years since, there have been 11 tropical storms. All of these terrestrial weather events, have a massive impact on the region's ecosystem, something you can see reflected in the aquatic fauna of the region.
Hi, my name is Kelsey Simpson, and I will be sharing with you how aquatic fauna helps figure out climate history of St. John's, Newfoundland. Aquatic fauna in St. John's, Newfoundland can be very helpful in figuring out the climate history of this region. The main aquatic fauna we will be focusing on are the fossils that have been found in this region. Fossils are able to help us understand the climate change by comparing and contrasting what animals and plants once inhabited that region. For example, plant microfossils, trilobites, and atriarchs are the most common fossils that are found in eastern Newfoundland. Plant fossils typically leave behind more helpful information to climatologists because they are, quote, the masters of taking what's available to them and using it to their advantage, unquote. In simpler terms, plant fossils tend to show more evident evolutionary traits that are always based on their current surrounding area and can show how that area has changed over time. The different types of fossils that are typically found in the area of St. John's, Newfoundland typically consist of the plant microfossils along with less abundant inarticulate brachiopods, graptolites, and hyolithids. St. John's, Newfoundland has fossils that are useful for dating rocks of the Cambrian, Ordovician, and Silurian systems due to those specific organisms having a high rate of evolution during each of those periods. The fossils from the Cambrian period have more in common with Norway, England, Sweden, Wales, France, Germany, Spain, and the Czech Republic than Western Newfoundland. That is due to the two areas being in two different climatic zones, in each on the opposite side of the ancient ocean called Lapiteus. The discovery of this ocean is partially credited to the rocks in the area.
Radiometric dating, as spoken by Chris Delameter. Radiometric dating is the process of dating rocks via radioactive isotopes they may contain, utilizing either short-life radioactive elements like carbon-14 or long-life elements and their decay products like potassium-15 and its respective decay product argon-40. Because the rate of decay in all radioactive isotopes is static, meaning it doesn't change based on time or external influences, it can be used as an incredibly accurate means of dating samples. Thanks to radiometric dating, we know that Newfoundland and Labrador, Canada have some of the Earth's oldest igneous rocks on the planet, many dating back almost 4 billion years. The reason these rocks can be so well dated is due to their igneous nature. These rocks, such as granite and basalt, are formed when molten hot materials cool and solidify over time. Radioactive isotopes from deep within Earth's interior remain inside these rocks and allow us to date them today.
My name is Theodore. Thank you for listening to our presentation. Historical data, such as the topics presented here, help us understand how climate change has affected St. John's, Newfoundland. These individual topics, historical sea weather, historical terrestrial weather, aquatic fauna, and radiometric dating, all tell us how climate has changed over thousands of years, some even dating back to millions of years, such as our fossils and rocks. These topics can forever help climatologists understand how to predict the pattern of climates for the future. Thank you for listening to our presentation, and I hope you enjoyed. Are there any questions about any of our topics?